I'm going to talk about renormalization group flowing between percolation and Nishimori. Before I start, let me introduce you to the team. So first of all, Guyi and Simon, who supervised my master thesis, and now Simon is supervising my PhD thesis. And also Romain and Andreas, who we got into the team to get some analytical understanding for the conformal field theory underlying our problem. Okay, so what are we actually looking at? What are we interested in? We are looking at long-range entanglement, and let's just say, because long-range entanglement in general is a useful resource for quantum computing. In particular, we are going to look at GHZ states. So you probably know GHZ states. It's just this superposition of zeros and ones. You can also think about them as a generalization of Bell pairs. And throughout the talk, I will visually represent them via these arrows. And GHZ states being this superposition of two macroscopically distinct states, we can also name them cat states. Okay, so they can be quite useful, but so how can we actually create them? So the naive approach to create such GHZ states would be a unitary protocol where we start in a product state and then we apply a Hadamard gate and a CNOT gate to get a Bell pair, and then we can just add one more CNOT gate to create a small cat state, a small GHZ state. Now by applying even more CNOT gates, we can kind of grow this cat state into a larger cat state and create this very large GHZ state. Note that for this protocol, the entanglement creation is kind of bound by this light cone pattern, and thus the circuit depth always scales with the number of qubits. So technically, we could reduce the scaling to something like square root of n or log n when we go to 2 dimensions or when we have the ability to use long-range CNOT gates. But we will always have some kind of scaling with the number of qubits. And if you want to reduce the scaling, we could look at a non-unitary protocol, which will be the basis of the talk. So again, we start in a product state, and now we apply 2 layers of rotational ZZ gates to create a cluster state, which we then kind of use as a resource and measure every second qubit. And measuring every second qubit, so using every second qubit as an auxiliary qubit, we can prepare the other qubits that we don't measure, the system qubits, in this GHZ state. That is, if we get lucky and we get the measurement outcome that we want on every measurement. But if we, for example, get one measurement outcome that we don't want, we will end up with a domain wall in our GHZ state, or a syndrome. So we will end up with a glassy GHZ state. However, in general, this is not a problem, because these measurement outcomes, we can just record them and we can classically decode our glassy GHZ state and then take that information and do some corrections on our quantum state to recover the perfect GHZ state. Okay, so the advantage of this protocol, of course, is that now we just need a finite number of layers in our circuit. So we reduce the circuit depth. And of course, the disadvantage is that we use every second qubit just to prepare the state. So we lose half of our qubits. So I introduced this circuit in 1 dimension, but we can also do this in 2 dimensions. For example, on such an RBIM chip, where here we have then the system qubits on the nodes and the auxiliary qubits sitting on the bonds. And the protocol really looks just the same. So if you look at a snippet of our circuit, it looks just as our 1-dimensional circuit before. The only thing that gets more complicated in 2 dimensions is essentially the decoding But yeah, we are still able to do this using something like MWPM or a tensor network decoder or whatever you want to use. So yeah, talking about implementing this on a two-dimensional IBM chip, we of course have to talk about yeah, that current devices are quite bad and they have all kinds of errors. So we might want to ask the question of whether or not our monitor protocol even works in a faulty settings when we have some kind of imperfections. So this is what we want to do. So yeah, let's introduce the imperfections that we want to look at. And the first one being some imperfection that we apply to our rotational ZZ gates. So we call this coherent gate error. And essentially what we do is we take this pi over 4 right here and we perturb this pi over 4 to, yeah, to an arbitrary angle t. And essentially, yeah, we perturb this rotation of this RZZ gate. And then the second imperfection that we introduce is qubit loss. So we take our perfect square lattice and reduce the number of auxiliary qubits in it to we can essentially, from a statistical mechanics picture, we can view this as lattice defects. So yeah, note that, for example, this heavy hexagon IBM chip, you can also think of it as a square lattice with some auxiliary qubits missing. So now let's look at these two imperfection sources, so coherent gate error and qubit loss separately. And yeah, this coherent gate error was already studied before in this paper by Gouilly and Simon. So in the next few slides, I will give you a short recap of the most important results. So as I told you before, we essentially take this pi over 4 and we now allow it to also take different values. So our parameter t goes from 0 to pi over 4. And with that, essentially, we go from weak to strong measurement. Remember that this gate is essentially what couples the system qubits to the auxiliary qubits. And measuring the auxiliary qubits then results in weakly or strongly measuring the system qubits, depending on how strong the coupling between the qubits was in the first place. If our coupling is very weak, or if there's no coupling at all, we will not be able to create long-range entanglement. But if it's strong enough, we will end up in our GHZ state and we will be able to create this long-range entanglement. And somewhere in the middle, at least in 2 dimensions, there sits a finite stability threshold which separates these two phases. Right, so a different perspective on this may be that I told you that we use this cluster state essentially as a resource. And over here, for t equal pi over 4, we are using the perfect cluster state to measure. And then essentially along all of this axis, we are using an imperfect cluster state. And interestingly, even though over here we have an imperfect cluster state, we are still able to create this long-range entanglement by measuring the auxiliary qubits. Okay, so is there some interpretation to this coherent gate error? Yes. For that, let's write down the wave function of the post-measurement state. So essentially, this is the state that we get out of our circuit. And we write this down in terms of beta, which is some parameterization of t, and in terms of Sij, which are the measurement outcomes of the auxiliary qubits. And now, following Born's rule, we can calculate the probability to measure into such a state to be e to the minus beta sum over Sij sigma I sigma j, which you might find familiar if you remember your statistical mechanics course, because this is just the partition sum of the random Ising model, where now the measurements in our quantum circuit correspond to the bond couplings in the random bond Ising model. To make this a little bit more qualitatively, let's compare these two models. So on the top here we have our quantum circuit where we go from weak to strong measurement as we vary t from 0 to pi/4. And now on the bottom I will draw the classical random bond Ising model correspondence. So here we go from 0 to beta equal infinite, and thus we go from high temperature to low temperature, and the phases go from paramagnet to ferromagnet. If we draw this in the phase diagram for the random bond Ising model, this looks something like this. So we have the disorder probability on the x-axis, the temperature on the y-axis, and our ferromagnet and our paramagnetic phase separated by this phase boundary. And then somewhere along this line, Nishimori 40-something years ago solved this system analytically along this Nishimori line, which goes like this. It's defined as this relation between P and beta. And this point where it crosses the phase boundary is called Nishimori point. And now it happens that our quantum circuit, which we just parameterized by this one parameter t, exactly locks onto this line. So when we vary t from 0 to pi/4, we kind of move along this one-dimensional line in this two-dimensional phase diagram. And this is particularly interesting because the renormalization group flow is flowing out of this Nishimori point. So if you don't know, renormalization group flow is essentially, imagine you're sitting exactly on this Nishimori point, then your system behaves like a Nishimori system, you're in the Nishimori universality class. And if you now perturb your system a little bit, maybe towards this direction, for very large system sizes, you will immediately start to behave like a clean Ising system. So you switch universality classes. That's meant by the RG flow flowing out of this Nishimori point. And now why this is interesting is because in our quantum circuit picture, we are kind of locked onto this line. So we don't care about the RG flow flowing out of this line because we are locked onto it by default. And that makes it very easy to study this physics in our quantum circuit picture. Okay, so let's get to the second imperfection, qubit loss. So we parameterize this by using one parameter p bond, where p bond equal 1 means we have a perfect lattice, and p bond equal 0 means we essentially have no lattice anymore. And we want to first consider this for in the absence of the coherent gate error, so for t equal pi/4. So if we look at a lattice example for a large p bond, you might see something like this, where every qubit is connected and we have this one large cluster which spans the whole system. And since we are in the case where t is equal pi/4, we know that now every qubit that is connected will end up in a GHZ state. So in the end, we will have a long-range entangled state for this example. And if we look at an example for a small p bond, we might see something like this, where we have many small clusters which are globally disconnected, but each of these clusters will form a small GHZ state of itself, but there is no global connection between them. So this would be an example of a short-range entangled phase because, again, there's no global connection. And actually, I learned a few weeks ago from Robert that this is actually the reason why the cluster state is called cluster state. Yeah, by thinking about this, you can argue, or you come to the conclusion that the question of whether or not you have this long-range entanglement or short-range entanglement just comes down to the question of whether or not you have this global connection in your lattice or not. And this is exactly the question of percolation. So if you don't know, percolation is give me a lattice, give me a probability for dilution, and I tell you, do I have a globally connected lattice or not? And yeah, especially for square lattices and bond dilution, this is very well understood. And we know that the percolation threshold sits exactly at 1/2. Okay, so now we discussed kind of this coherent gate error and this qubit loss separately. Now let's bring them together. So what happens? So again, on this y-axis, we have our p-bond with this percolation transition. And on the x-axis, we have the parameter t with this coherent gate error with this Nishimori transition. And now we want to know how are these two critical points connected, and yes, specifically, like how does the criticality behave on this line? How does the criticality change as I move from Nishimori to percolation or vice versa? So this is what we want to do. Now let's make a slight shift towards how we do that, which is by tensor network simulations. So yeah, let's talk about how we actually do our simulations. So we represent the state that we get out of our circuit, so the post-measurement state, as a PEPS, as a projected entangled pair state, where on the nodes we have delta tensors, and on the bonds we have these bond matrices, which depend on the measurement outcome S of that particular auxiliary qubit, and also the coupling strength or measurement strength beta. And now, now we can go ahead and calculate the norm of this state. And theoretically, we could now go ahead and just contract this whole two-layer tensor network, but this might get a little bit numerically complicated. So we can do one more analytical step to simplify this by flattening this two-layer structure into a one-layer tensor network, where again we have delta tensors on the nodes, but now the bond matrices change a little bit. And this is now a fairly easy to contract tensor network. Yeah, but we can also put some observables in between our two layers, and then the bond matrices here change a little bit depending on what type of observable you put there exactly. Okay, so how do we actually contract this now? We take this two-dimensional one-layer tensor network, and we contract this by MPS evolution. So what's MPS evolution? Essentially, we start at the bottom of our tensor network, we construct a matrix product state, and then we construct a matrix product operator, and we contract these two. And we do that many times until at some point we contracted the whole tensor network, which will give us some number, which we want to calculate. Okay, so now let's talk about what we actually calculate. So what observables are particularly interesting. And I want to talk about two of them. The first one being coherent information. And to understand this, let's step back a little bit. So I told you that in our circuit, we essentially use the cluster state as a resource. And then by measuring the bond qubits, we prepare our GHZ state. But we could also go an alternative route, and we could measure the side qubits, and this would prepare a surface code state. So in a sense, these two things, so the protocol to create our GHZ state and the surface code, are dual to each other. And their duality is of such nature that essentially acting Z operators on two neighboring sites in our circuit picture is dual to acting a Z operator on a bond in the surface code picture. And with keeping that in mind, let's draw this tensor network, this monitored circuit, where we fuse the boundary qubits. And when I say fusing, I mean essentially taking the coupling between these qubits and drive the coupling to infinite, such that all of these boundary qubits essentially become one qubit, 1 degree of freedom. And now we calculate the ZZ correlation between these boundary qubits. Without changing this observable, we could now just put some identity operations there. And now in our surface code picture, interpret kind of neighboring ZZ operators as Z operators on the bonds to get something like this, which looks very much like a string operator or a logical operator in the surface code picture. Right, so this parity of our boundaries defines a boundary bit. And if we calculate the classical entropy of this boundary bit, then this is exactly equal to the quantum coherent information. Why exactly are we looking at this? So couldn't we just do some mutual information or ZZ correlation, which is a little bit more or much more straightforward? Yes, but coherent information has a very nice property, namely that the scaling dimension is 0, which means it scales like a Binder cumulant. And that makes the coherent information extremely powerful to use for finite size scaling analysis to not only extract the location, but also the critical exponent, which is what we want to do. So yeah, to convince you, let me show you data for a benchmark. But for that, let's define a benchmarking sandbox. So if we measure our circuit and we run our circuit and measure it, we will get random measurement outcomes. Random measurement outcomes are not that great if you want to benchmark something. So being theoretical physicists, we use our infinite power over nature to change these measurement outcomes to exactly what we want. And this makes our circuit now map to the ferromagnetic Ising model, which is awesome because, of course, the ferromagnetic Ising model is very well understood and we know everything about it. For example, what's the critical inverse temperature and what's the critical exponent nu. And following our mapping also then, of course, what is the critical coupling strength. Okay, so equipped with this benchmarking sandbox, let's go back and now plot the coherent information for this circuit model, which now maps to the clean Ising model. And here's how it looks. For system sizes up to 256, we get this almost step function-like behavior with this very, very clean crossing point at the critical point. And if we do some finite size scaling, we also get very nice collapse. And note that by system size, I really mean here that we have a system size of L by L, so 256 times 256 qubits. Or in a more quantum information language, you would say that what I call system size is something like a code distance. And we need these large system sizes to really see the change in the criticality later. So yeah, let's go to the second observable, which we call boundary entanglement entropy. And to motivate this, let's go back to how we contract our tensor network. So I told you that we do this matrix product state evolution of our 2 plus 0 dimensional quantum circuit. But this kind of evolution we can also view as a 1 plus 1 dimensional imaginary time evolution, because we essentially take our 2 plus 0 dimensional circuit system and we view this as a 1 dimensional system which we evolve in time. And we don't want to do this now for this squared circuit, but for a very, very long stripe. And we want to evolve this for how long it takes to, at some point, hit a steady state. And this steady state, then, we want to take to calculate the entanglement entropy of it. So let's again look at an example for our benchmark. So now for this system that maps to the clean Ising system exactly at the critical point. And here's how it looks. So on the left, the left part of the plot shows the entanglement entropy, as a function of the cutting position, so where exactly I cut my one-dimensional chain. And then the right plot shows the entanglement entropy for a bipartition as a function of the system size. And we can now take both of these plots and fit the central charge to it following the Calabrese formula. And we get something like 0.505 for the right one and something similar for the left one. And both of them are reasonably close to the central charge that we know from the Ising conformal field theory, which is 1/2. So at this point, we are kind of satisfied with our benchmarks, and we want to go back to the system that we really want to study, which is this phase diagram that I showed you earlier. So let's shift back and get to the numerical results. But before I do that, let me quickly remind you what we actually were looking at. So we had this phase diagram where on this y-axis we had this percolation transition, and on the x-axis we had this Nishimori transition. And we wanted to ask the question how the criticality between these two kinds of critical points changes as we move along this line. So let me now replace this sketch of a phase diagram by actual data. So it looks kind of the same. But now this is real data, and it's very high precision. And also this is color-coded in a way, which I will explain in a few slides. So how do we get this data? Let's look at an example transition. So let's look along this percolation transition over here, because for percolation, we kind of know everything. And we want to plot the coherent information along this cut through the phase diagram. And it looks something like this. We can do a finite size scaling analysis. We do the scaling collapse. And from that, we extract both the critical location and also the critical exponent. And for both of them, we are very, very close or exactly on top of the analytically known values, which is for the transition 1/2 and then for the exponent 4/3. So we are, again, kind of satisfied with our results. And we can also do some residual landscape plot, which shows you how good is this collapse for what kind of parameter pairs. And when I was doing this, I noticed that in Julia, which is what we use, there isn't really a nice package for finite size scaling. So I wrote this package called scaling collapse. So in case you want to do finite size scaling in Julia, you should definitely use this. Right. So now that we talked about this percolation transition, and we see that this very, very much agrees with what we know from analytical results, let's look at the Nishimori transition and do the exact same thing. So we cut along here, and again, we plot the coherent information. And we see that this looks very, very similar. We again do a scaling collapse. We again extract the location and the critical exponent. And now, of course, we get some different location, but also we get a different critical exponent, which will be interesting later when we look along this critical line. Again, we can do this residual landscape plot. Okay, so what we want to do now, so I told you that so far we looked at the percolation transition and this Nishimori transition. And now what we do is essentially we take many, many cuts through our phase diagram in this radial pattern, and we do exactly what we just did. We calculate the coherent information, do a scaling collapse, extract the location, and also the critical exponent. And so where's the RG flow? In the title, there's something about the RG flow. And to come to this point, I now want to plot the critical exponent as a function along along this line here, so along the critical line. So we parameterize this by this angle theta, where theta equals 0 now is the Nishimori transition, and theta equal pi over 4 is this percolation transition. And if we plot this, we get something like this. So exactly at the Nishimori transition, we have this value of 1.51 something. And then as we move along the line, this stays very, very constant until at some point, very close to percolation, this drops to the percolation value of 4/3. And this is, why we say that the RG flow must go from percolation to Nishimori, because imagine you sit on this percolation point. If you perturb your system a little bit and you move there, your system immediately starts to behave like a Nishimori system, because this critical exponent suddenly jumps to the value of the Nishimori critical exponent. And on the other side, if you sit at the percolation point and you perturb it a little bit, your system doesn't even see this because everything stays the same. And note that, the fact that this is not a step function, but some smooth function, comes from the fact that this is still with finite system size data. So if we would go to infinite system sizes, we would probably see a step function there. Okay, so now let's also talk about the boundary entanglement entropy at some critical points along this line. So let's first look at the Nishimori critical point. And if we plot this looks something like that. So the left plot is essentially what I showed you earlier, where we had this entanglement arc. But now I just rescaled the x-axis to collapse this to a straight line, where now the slope of this line is this coefficient c. Also look at some point in the middle of this critical line, and we see that this looks pretty much the same. And if we look at a point, at the percolation point, we see that now something happens and it looks very different. But now if we look at a point very close to percolation, we see that it again looks very different. So this is a little bit confusing maybe. So let's again look along this critical line. So now let's plot the slope of these linear fits along this critical line. Yeah, what we see then is something like this. So going from Nishimori to percolation, we first stay kind of constant, then we have this peak, and then we drop off to the value at percolation, which is analytically known to be 0.57 something. And if we now plot data for different system sizes, this gets more interesting, because it seems like this peak is shifting towards the percolation point. And if you would extrapolate this to infinite system sizes, you may argue that this peak actually then sits exactly at the percolation point, and you again have some kind of step function behavior where we have this peak exactly at the percolation point. Right, so from this plot again, we can argue that the RG flow must go from percolation to Nishimori, because again, when we sit at Nishimori and we perturb it a little bit, the system doesn't really change its criticality. But if you sit at percolation and you change it, then something drastic is happening until at some point you flow into the Nishimori criticality. At this point, I can now also explain to you what this color coding in the phase diagram was. So this color coding is exactly the value that we have here on the y-axis, so the C entanglement prefactor, where we have this constant value throughout most of the line, and then this peak very close to percolation. Yeah, so let me summarize what we did. So we started by studying the stability of this non-unitary circuit for GHZ state preparation. And we noticed that by weakening the measurements, our system goes through a Nishimori transition. And by applying Qubit loss, our system goes through a percolation transition. Using the coherent information, we mapped out this phase diagram, and we calculated the critical exponent along the critical line, and also this entanglement scaling prefactor along the critical line. And both of these plots led us to the conclusion that the percolation critical point must be unstable in favor of Nishimori. Yeah, so this is the result of our work, I would say, and this is also the end of my talk.